So welcome everyone to our Friday seminar. It's a pleasure to have Maria Schuld from Xanadu and the University. Oh, I've never actually tried to pronounce this. Maria, can you help me?
KwaZulu-Natal, yeah.
And she'll be telling us about some topics in quantum machine learning. So please take it away.
Cool. Thanks very much, Chris, for the opportunity. And it's wonderful not to travel and be jet lagged, just to sit here in my own home. When I prepared the slides, I looked at the title again and I thought, this doesn't sound like terribly interesting. So I should have done a bit of a better job. But actually what I want to do in this talk is something that I find really exciting. I want to convince you of one thing only, and that is that in quantum machine learning, or most of quantum machine learning, the way you encode your data into your quantum computer is probably 95% of the job. So after that, if you do that well, you're probably done, you have solved your problem. And in the last couple of slides, I will refer to a paper that somewhat hiddenly makes that point. And that was written with a couple of collaborators. So you see Seth Lloyd, Arusa Ilyas, and Josh Isaac and Nathan Killeron. The last three are also from Xanadu. And let me first give you an idea. So I was told that most of the audience has a background in quantum computing, more or less, and has heard maybe of quantum machine learning before. Let me first tell you where this talk will be focusing on and what it won't talk about. So the intersection of quantum computing and machine learning has been like growing, or a lot of like literature has been growing in the last couple of years, and there are lots of angles, and you might have seen this little graphic here that's often cited. You can kind of distinguish the approaches that people take by the type of data that they use. Is this quantum data? So for example, measurements from a quantum experiment, or even quantum states, or is it classical? And then is your algorithm or your computing device classical or quantum? And there are lots of interesting intersections. So even the purely classical perspective in the upper left corner is really fruitful. For example, people are using machine learning and neural networks to describe quantum states here. So purely classical, but a lot of interesting intersections. In the lower right corner, you see the quantum case, which is largely unexplored, but lots of people say that this might be the future of quantum machine learning, actually, that quantum computers produce information and then they start analyzing it as well. And then only after the measurement, you get a result out. The quantum so the QSI case is also quite interesting, because that's like using classical machine learning maybe on data you've got from your lab in a quantum experiment. And I shall be focusing on this part. In short, how can we use quantum computers to do machine learning, actually? And I've been doing that for many, many years for now. And there's another thing that I won't talk about. Sometimes the term quantum machine learning, even if we like limit it like that, is very confusing, because lots of people in the headlines speak about something, but they actually only mean a part of the literature that's out there. And I think you can really nicely distinguish these two different types of quantum machine learning algorithms. There's the good old quantum computing perspective, and this was very much how it started in the first years. And how those quantum machine learning algorithms work is you take a textbook in machine learning, you take your favorite algorithm. Most people will pick neural networks for a reason that I can't understand anymore, although I did it myself very much for a couple of years. And then you kind of just look into your quantum computing toolbox and see, what can I use? So for example, we can reformulate this machine learning problem as a linear algebra problem. Can we now use an HHL algorithm on a quantum computer to solve these linear equations? And then a lot of the papers will stay very much within the ideas of quantum computing, do complexity analysis. They want to speed up machine learning. There is a growing and very, very interesting part of literature that looks into it from a very different perspective, from a near-term quantum computing perspective. There, you start with a device. So you say, I've got a quantum device. It might be noisy, it might be small, not much happening here. What machine learning can I do with that device? And you don't necessarily want to speed up things. You might just want to develop a new class of machine learning algorithm that hasn't been there before. You want to see, well, honestly speaking, you actually want to see, is there an application for your quantum device that you can sell in the end? And so what I want to go through these 4 points, and maybe just as an executive summary, what do I want to say? Because every one of those sections should actually have a message in the end, and I hope that this becomes clear. In the machine learning basics, I just want to tell you that machine learning is centered around the concept of a model. And a model is basically just a mathematical function that maps from data to predictions. And the second point I want to make here is that the task of machine learning is to find models that generalize well. So basically you only have very little data, you've got very little information, and you want to like make maps or find maps that are actually very useful in real life. And then the second bit is also still like about classical machine learning. It wants to say that there's this concept of feature maps. You can understand these models or these maps as mapping from data to an intermediate feature representation. That could be an infinite dimensional vector. In theory, often people think about it as living in Hilbert spaces. And if you do quantum computing, you immediately like start thinking, okay, there's something interesting here. And then you map to your predictions. And then I introduce into like the workhorse algorithm of near-term quantum machine learning, which are variational circuits. The idea here is just, okay, let's use our quantum device, tune some parameters that we have, physical parameters or turning angles of qubits, and learn basically a map or computation from that maps inputs to outputs or data to predictions. And then finally, I want to like put all those blocks together and say like, why does this now lead me to the growing conviction that data encoding into this device is the most important thing? And I'm just saying this is, I don't know if it's controversial, but I don't think lots of people see it like that, because everyone's always looking, you know, they just put the data encoding aside, look at the quantum algorithm itself. Okay, let's start. Interrupt me anytime. So there are three ingredients to machine learning. The first ingredient is data. And I will only talk about supervised learning here. In that case, you've got some inputs, X, and some outputs, Y. The Ys would be what I call the predictions. And there's some relationship between X and Y that's unknown, that these data are usually produced by real life, so to speak. There's a regression problem where Y is continuous, and there's classification problems where Y is binary, as you can see here. The second ingredient of machine learning is a model, and this is actually the word model is, I know it's used by lots of disciplines, but in machine learning it's almost as complex as a quantum state. For us, this is all like very easy after a while. We have a clear image, but it takes ages to understand that. So here, for example, in the regression case, we could just use a linear model, or here in the classification case, like the simplest model is probably just a step function. And this is what we talk about a lot. And usually in machine learning, in most algorithms, not all of them, the model is parametrized. So it depends on your inputs, obviously, but it also depends on a set of parameters that are always called theta. And these parameters are usually defining a whole model family. And you now start like using optimization algorithms to find a model in that family that suits your purpose best. And now this is the third ingredient. What does best actually mean? And this is defined by a loss function, which you also have to set. This doesn't fall from the sky, but there are lots of standard loss functions. Most of you probably know mean squared error loss or something. And the loss compares what your model says, the prediction, with what actually the data that you have says, and will basically, if you average over the loss of all data that's possible, you get something like your expected loss. And this is always, so when I talk about loss, expected loss, this is always a quality measure for your model. So how well are you actually doing with the one you picked? And then you can actually very nicely formulate the goal of machine learning. This is maybe not super central, but I talk a lot about generalization. So, so this is just like an interest or a good point I want to make, and completes the picture maybe. You can now say the goal of machine learning is to minimize the expected loss of a model. So if on the x-axis here, you've got plotted a lot of models. So every point here is a different model from a family, because I tuned through the parameter. Then you can plot this, what I just said is the average over the loss, so to speak. So the expectation of this loss function over all data that you could get. So this is like your quality of the model. So if you see this plot, you would definitely pick like this model here or this model here, because it minimizes the loss. So lower is always better. So, and this is like also like the theory of machine learning always says it's like, you know, risk minimization, and risk minimization means expected loss minimization. So this whole like neural network will be your model here. This parameter will be your weights if you work with those. And this minimization is then your stochastic gradient descent algorithm that trains the weights. And then lastly, just a few comments. Obviously, you can't really like, so this thing here is really hard to compute because you have to integrate over all your data, always a bad idea. So what you do, you get given a couple of data samples and you kind of approximate this function that you don't know and you can't access, this black function here with the green function, which is the empirical loss. And this is just the average loss over all the data you have. And now here's the big problem of machine learning, this green function here, that is what you have access to, and the black function might not always give you the same model. So look at this point here, the green function, so the data you see might suggest this is your best model. Meanwhile, it's really, really bad in real life because if you get more data, you will see it's doing very badly. And maybe like a model here will be a lot better. So this is the big problem in machine learning. You have to like find something and optimize something that you don't have access to. So you try to find proxies over and over. And this is also known as overfitting. So a solution here will be a solution that fits perfectly well in the training data, but might not really look like the trend. Yeah, and the last bit is how can you actually like know that you were doing well with this green curve that you have access to? You just put a bit of data aside, which is called the test data, and it gives you another curve, which you hope is closer to the black curve. So basically, you minimize on the green curve, and then you check with the pink one, okay, do we think we're doing well on the black curve that I don't have access to? And this whole thing is called generalization. So generalization means training a model on green, but trying to do well on the black curve, which means generalize well to unseen data. So as a takeaway, as I said, like 2 points. So first of all, the model is essential as a tool in machine learning, and the ideas or the task of machine learning is to minimize the expected loss of a model, so the quality, or increase the quality of a model over a small set of data, but you want to do well on all possible data. And a good model will then generalize well. So that's very important because in the next step, then we'll use quantum computers as these machine learning models and train them. The second little piece of machine learning that I need, so to speak, is maybe more a perspective on those models. So it's called, well, they're called feature maps. And in some sense, you can understand machine learning models as mapping inputs to features and then doing kind of implementing a model, so doing an intermediate step. So instead of like, so here I plotted a bit more interesting models, instead of like doing this thing here, you would first like map X to a feature space. So this could be like a vector, for example, and then apply a model. And very often in this view, you could say the whole, basically I outsourced the whole complication here of mapping X to very, very beautiful features that tell you a lot about the prediction. And then this model here can be very, very simple. I try to like show this in these graphs. So your relation between X and phi of X might be very complicated, but afterwards your relation between phi of X and Y is actually very simple. So once you've done this here, you've actually completed your job. And just for those of you who do machine learning, just how does it fit in? Because it's maybe not, you know, a textbook wouldn't start with this type of approach or idea. So this is more for people who now use neural networks, for example. So neural networks are often just depicted in this graphical notation. And what this means, you have a four-dimensional input vector, so 4 nodes. And then each of these connectivities just mean 2 things. You do a linear transformation and then a nonlinear transformation. So basically you multiply a matrix to these 4 inputs. And then on each of the outputs, which will be here, 2-dimensional vector, for example, you apply some nonlinearity. So a neural network is basically just a chain of linear transformations and then you know, scalar nonlinear transformations. So how does this feature map idea work here? You can say that the neural network, what it does in all these layers up to just about the last one, or last but one, is just extracting features, so that in the end here, these 2 bits of information that are in these nodes in this representation will actually already have all the information that you can very easily now extract a prediction. So if you feed an image and then you want to know is then AND or B on this image, in the end, for example, if this number is bigger than this, it will be an AND, or otherwise it will be B. So like the feature extraction has happened at the beginning. And as you know, in deep learning and in modern machine learning, actually you can look into neural networks and you can see how these features look like that you extract. And you very often really extract visual parts of an image. So for example, a wheel of a car or something will be present somehow as information in this delay. But much more interesting, and now your quantum computing brain should slowly switch on. There's a whole class of model called kernel methods, and they were very popular in the 90s. There was no neural networks in some years of the 90s, and it was only kernel methods. The most famous kernel method is a support vector machine, if some of you have heard about it. And the idea is that you take your data points. So for example, blue and red are here different classes of data. So for example, images of ants and images of bees. And you map, so mathematically speaking, you map this data to a really high dimensional feature space. So very often your feature space will be actually infinite dimensional. So your computer doesn't do this map, but it's just a mathematical construction that helps you understand what your model is doing. So you map your data into high dimensional, exponentially large, infinite dimensional Hilbert space. So the theory of kernel methods very much is rooted in Hilbert spaces. Because the reason is that models in the end take inner products of these data points. So if we know like a space with an inner product and a couple more properties will be in Hilbert space. And then after that, once you are in this really high dimensional space, you only have to do something that is very simple, which is a linear model, apply a linear model. Linear models would just be to multiply your huge vector. So I always try to like write a bit of a mathematical like picture description here. You take your really humongously large vector and you just like multiply it with the weight vector. This is only, just as a comment, this is only the mathematical description. In real life, again, you wouldn't like really multiply these infinite dimensional vectors, but it's equivalent to what you do actually in a kernel method. And now, so it's actually very simple now to say, okay, or maybe let me give you like a little sneak peek why I think data encoding is so important. If you think of what happens in data encoding in a quantum computer, you map data to a quantum state, and a quantum state lives in an infinite dimensional or an exponentially large Hilbert space. So what you're doing is this feature extraction step. When I say this is the most important step in machine learning, because after that, most things are easy. This is exactly what you're doing in encoding data into a quantum computer. But I explain this a bit in more detail now. Yes, so coming now to proper machine learning. So I said the workhorse of quantum machine learning are these variation circuits. The concept comes from quantum chemistry. I was speaking to one of the authors of this paper who was telling me the idea to this paper was actually that they went to the lab, they wanted to do or invent an algorithm that the lab could implement on a real quantum device. That was like in 2013 or something. And the lab or the experimentalists were always saying like, we can't do this, we can't do this, we can't do this. And then they said, okay, what can you do? And they said, we've got these control fields and we can tune them. Okay, so they said, then let's just tune control fields. So this is the idea of variation quantum circuits. You know, quantum computing, you know, this diagram. So this is basically just a general quantum computation represented by a unitary. But the difference in variation circuits is that you assume this unitary is parametrized. And what these parameters are can change from device to device. So if you have a, I don't know, a laser field that tunes some qubits in whatever setup, the strength of your laser field could be that, or strength of a magnetic field, or whatever it is. In a bit of a more abstract model, this is often, for example, the rotation of an angle of a qubit, or the phase of you know, a Z rotation of a qubit or something like that. You take measurements and you define a cost on that measurement. So you say, how well were my measurements doing in the objective that I had? And then you use a classical device to find better control parameters. And if you're working in experimental physics, this is like a very typical control setup. So there's actually nothing new, but to utilize this in a machine learning sense, to understand things as models, to do optimization, to use the tools of machine learning that we have with like really large scale optimization is kind of something new and is very fruitful. if we use this variation circuit, so at the moment I've said it depends on some parameters. So this already clicks a little bit because it sounds like, you know, this model family that we can tune. But for machine learning, for quantum machine learning, we need one more step. And if you see here, I just replotted this picture. We also have, you know, our model has to depend on X, otherwise it's usually not machine learning. So if we look at this model, let's just for now define it just as the expectation value of some quantum observable. So what's going on here is literally in the experiment, the sigma z means you measure the state of a certain qubit or a couple of qubits after you apply a circuit u of theta. And you do this a lot of times and then you average. So this is what this mathematical expression means. So it's an expectation over the quantum observable party z after applying a circuit. So it's basically just an average measurement value what you get. And this is your f of theta. But so obviously you have to have your circuit now also depend on X in some sense. And how could you do this? The same way that you have the theta. So you could just take some of the thetas, put them aside and say, just initialize my thetas in exactly my X values, so exactly my data values. So if an image has a pixel that has an RGB value of like, I don't know, 230, and then you normalize it, and then you will basically use the rotation angle on a qubit that corresponds to this pixel value. So this is the idea. There's a very beautiful summary or overview article from Marcello Benedetti here that explains how to use variation circuits as machine learning models. And just lastly, just to switch again in this description to like a more optical way. So the way we can think about it is, and this is non-central, is we have a state preparation circuit that somehow encodes X, and then we have a model circuit that we train. So this is a bit artificially separated, but it's very useful. And then in the end, we measure something, and then we might post-process our predictions again. Mathematically, what's happening is this expectation value is kind of multiplying matrices onto like a unit vector, and then you take this like quadratic form here to get your expectation value. And I think those two papers were like proposing it for the first time actually to do this for machine learning. So this is like variation circuits, and whole idea of quantum machine learning here. I use my quantum device with tunable parameters. I take some tunable parameters to encode data, and then I use the rest to kind of learn a model. And a lot of people and a lot of work in quantum machine learning of this type has focused on this model circuit here. And what can we use as an ansatz for this model circuit? What's more powerful? What does entanglement do to your predictions? A lot of literature has also, and this is very beautiful literature actually, has focused on how can we train these models. So this classical feedback loop here, how can we get quantum gradients out of models? I want to talk about this, but this is like also something that I'm really interested in and active in as well. But however, what I'm saying is this is actually your entire quantum machine learning algorithm in some sense, the state preparation. So how does this work? Let's first talk a bit about what this circuit could be, because it's actually something that's not very typical, only there for machine learning, but you will find it in any quantum algorithm. You have to encode an input, right? Even Shor's algorithm has to encode some bits somehow. So this kind of like data encoding is very natural for quantum computing. And in some sense, you could even say any quantum computation is a quantum machine learning algorithm, because you can interpret it as a quantum machine learning algorithm in this framework. So old school quantum computing always does this type of thing. You have an input, you binarize it, or you just assume it's binary at the beginning. And then your circuit would just like flip the qubits that correspond to 1. So you would just have X gates on those qubits, and you associate your binary sequence with a basis state of your quantum computation. So this would literally be your quantum circuit in this sense. For those of you who, are very awake, so this idea in terms of machine learning is actually maybe not what seems like a very good idea, and then it seems like a very bad idea. So there's a bit of a discourse if you want to follow. What does this do? It maps every data point to a completely different unit vector. So what happens afterwards? You have data on a hypercube, on every corner of a hypercube. This is good for machine learning because it separates data nicely. You will always be able to draw a decision boundary, or like a linear model will always be able to classify your data. But why is it bad? The moment you have a new data point that you haven't used before, it will map again to a completely orthogonal basis state somewhere. So you have no clue which class it belongs to, because everything is like has the same distance in some sense to everything else. So interesting, but I'm not convinced that this is good for machine learning. A lot of quantum machine learning use this thing that I would call amplitude encoding maybe. So you encode your X into the amplitudes, or sometimes also the probabilities of a basis state. This is kind of an exponentially compact or logarithmically compact encoding, because you need n qubits to encode 2 to the n values in some sense, and even you can encode complex values, obviously. But your state preparation circuit will take quite a while, and especially the old school quantum machine learning or the more traditional approaches, I don't know, they're often very tricky, and when you read a lot of controversial discussions about it, it often hinges on this encoding, because so a lot of the exponential speedups they claim rely on the fact that I can prepare the state just like that. So then they come up with QRAMs or with like something. I personally take the stance, if you have classical data and you want to do quantum machine learning with it, you have to touch your data. So you will never be exponentially fast in anything that is in the data size, because you have to at least like load every data point into whatever QRAM you have, you know, devised. So I don't know if I'm too negative or, but so this is an interesting encoding. It allows you to do lots of linear algebra on your data, but yeah, it's harder to prepare, obviously, because this is arbitrary state preparation here. Yes, and then near-term people, what they use, as I said, is often like the rotation angles of qubits. So this is like an Rx rotation, a rotation of a qubit around the x-axis, and you can just encode your inputs into those rotation angles, and you get something that's still like unentangled, but you get a very high dimensional space vector afterwards, or quantum state that depends on your data. And then obviously you can go totally wild. So this is like, for example, a feature map from, sorry, I should have put the reference, I heard somewhere else, from an IBM paper about like quantum feature maps. They use something like an IQP circuit where they encode data into the diagonal gates, for those of you who know. Why do they use this IQP circuit as an encoding? They just basically think in quantum computing terms, they want to do something that's known to be intractable. So they say, okay, this is now encoding that's intractable in some sense. If it's helpful or not for machine learning is still an open question, I guess. And I'm almost there now to make this argument now. So I said before already, and hopefully like you will agree, that data encoding is in some sense a quantum feature map. So again, this feature map was like mapping data to large vectors. And what this circuit does, and sorry, I'm just saying like these two papers actually have noticed that. So if you want to see like this thought more plotted out, then look into those. I think they were like 1 month from each other and contained almost exactly the same proposal. So that was quite interesting that sometimes ideas pop up. So again, this first part of your quantum circuit maps your X to your feature state. And now here's an important observation. So I said before that in this whole class of quantum machine learning algorithms, you do this feature map, and even in the neural networks you do that, and afterwards you apply a linear model. So the only thing you do after you mapped your features is something linear. Think about a quantum circuit, the same thing happens here. This thing here is nonlinear in your X. It's a linear transformation, but it's nonlinear in the X. So that's super important. However, what you do after, whatever you do after, is linear in your state. So this is one very important point towards the argument. Why is why is data encoding so important in quantum machine learning? After you encoded your data, anything you do, except from the measurement, will be linear. So if you map your data onto a block sphere, the only thing you can do now is rotate your data. So what you basically do, you can just learn the measurement basis, but not much else. When I say the measurement introduces some nonlinearity, this is just a technicality. Obviously, when you measure, you do something quadratic. Why? Because, so think about this mathematical formulation here. You apply a matrix after this, so which is nonlinear in X. Now, after this, you just have a linear transformation, but then when you get out the expectation value, you kind of have this quadratic form here, like multiplying the quantum state from both sides. So there's a slight nonlinearity in the measurement, which distinguishes from this quantum circuit from the classical model. In all shortness, any quantum circuit that has this structure, and this is very, very general, implements a quantum support vector machine or quantum kernel method in some sense. And now here's the last little bit. And this is now from the paper I was referring to and that I think you also have a link to. Seth came to us, I think, after this paper was written here, this one here, and said, why on earth are you doing what you're doing? So why on earth, let me go back here, are you training this circuit and thinking about how to train it and whatever to learn this linear decision boundary? Why did he say that? He said, we know in quantum physics what is actually the measurement that distinguishes quantum states the best, or two classes of quantum states. It's the Hellstrom measurement. There's a lot of literature on this idea of that the maximally discriminating measurement is the Hellstrom measurement. I kind of switch a bit more to comic here, but if you encoded your data and you have it like in nice clusters of data, so this will be an ensemble or a density matrix of states, and this will be a density matrix of other states. And if you've got two you know, mixed states, and you can say like how to distinguish between them is the Hellstrom measurement. This is true. There are a couple of really interesting subtleties here, so which meant it took us actually quite a long time to work it out, because the statement, I have to say, has been made in an archive kind of note in 2008 by Sebastian Gams, and he also said, like, you know, quantum classification means Hellstrom. It's actually not entirely true. It depends on the loss function. This was why I was going through it. It depends on what loss function you take. So for a linear loss and a quantum model, as I just described it in the variation circuits, the Hellstrom measurement minimizes this linear loss. So you can show that. However, another loss function, for example, for those who know the accuracy of a classification problem, this might not be true, because you might have a data point from this class that's astray on the other side of the boundary. And Hellstrom will still find like kind of some average measurement decision boundary, but will have misclassified one data point, meanwhile another one might not. So to cut a long story short, there's a lot of subtleties hidden in there, and I think it's not as easy as just saying Hellstrom is always the best. Second problem is Hellstrom is, we tried for months, Hellstrom is efficient. There's an efficient algorithm you can use to implement it, but it's not near term, so you need hundreds of qubits for it. It's really a very hard construction of a measurement, and those of you who know about Hellstrom measurement might agree. So it's nothing that you will be able to do in the next years in the lab. So then, you know, you can look into other measurements that are very similar. So for example, maybe it's not the optimal one, but maybe you can also do a fidelity measurement. So you can just, like, instead of getting the trace distance between data points, which is kind of what the Hellstrom measurement does, and which is kind of like an L1 distance in your Hilbert space, you can get an L2 distance, which is the Hilbert-Schmidt norm, and you can like kind of measure the overlap between quantum states. So it's not optimal, but it's something you can do very quickly. So now there's the next step, or second step. Now when you say the measurement is now clear, so this one here is fixed, we know what to do here, we just do fidelity measurement. Now you say, like, okay, but now my encoding is really important, because what I want my data nicely clustered in my Hilbert space, because then my job is done. I can already distinguish between these pictures of ands and these. So what could you do? And that's the second step of this paper. Why don't you learn this part here? Why don't you make this S dependent on a couple of control parameters? And if you don't know what's the best encoding, you just learn the encoding. And that's what we started to experiment with. This is a kind of an example. So here you just take 1D data, like experiments in quantum machine learning are always laughably small. I apologize for that. And this is a simulation as well. You take your data, like 2 classes of data, but here you see it's not linearly separable. So blue is like enclosed by the red. And then you encode your data into like these Rx rotations here, but you have these Ry rotations in the middle that you can train. And what you get at the end is kind of like an embedded, so we call these embeddings actually, embedded input X in your Hilbert space. And since it's a single qubit, you can plot this nicely. So at the beginning, when you just have random parameters theta here, so random model, you see that these things are like randomly like distributed over your block sphere. And also here, this is the overlap between the states. You can see it's rather like arbitrary. And then you can train the model, and you can really learn nicely to separate these data, these data points. And you can see here that all of a sudden your data has structure. Afterwards, you do like fidelity or Hellstrom measurement, you can actually classify. Just for those of you who are interested, we also did this entire thing here is now 2 qubits. But now we did this with a classical neural network before, because we thought like it would be nice to do this with image data. This is also inspired by something that Andrea Mari has done before in quantum transfer learning. You take your data, you put it into a pre-trained ResNet. You chop off the last layer of the ResNet to map to a two-dimensional vector. You encode this into a quantum circuit. So what you get afterwards is an embedding of data into a quantum state that is hybrid. It's partially a classical neural network and it's partially a quantum neural network or quantum circuit. And here's again the data plotted now in 2D. At the beginning is arbitrary, you train, and this is very beautiful. See here so this is a plot of these x's here. What does the classical neural network learn to do? It learns to put the data classes in a very periodic structure. And this makes sense to us because we know that these rotations, you have some sine and cosine, so that they are very good at like distinguishing periodic signals. So this is like an interesting observation.
So could I just interrupt quickly on that point?
Yes.
So in this, so this network, you're learning the weights in the last layer of the classical network, and
good point, yeah.
And the theta is at the same time.
Yes.
Yeah. Okay. All right. Thanks.
And this is actually my last slide. Good one. Because so why can we do this so nicely? So part of my day-to-day job, actually probably 50%, is like working in software development. You know, there are a lot of quantum computing languages like Qiskit or Cirq. And at Xanadu, we're developing, or have been for 2 years, developing a language for quantum machine learning, a software framework, which is called Penny Lane. And the idea of Penny Lane is that you understand the quantum part of your computation, the quantum optimization, just as a little node in a big chain of machine learning. So for example, you take a TensorFlow or PyTorch network, and then you kind of exchange a little part of it with the quantum computation. So this type of thing is very, very natural in the software framework. And that's actually what I want to conclude with, is that if you want to like actually try this yourself, and there are also lots of other demos, but there's a big implementation of this in Penny Lane that you find on PennyLane.ai QML demos. A little warning, everything bigger than 1 qubit or 2 qubits you want to do is excruciatingly difficult. Although you have to say that these parameters here you learn are 1024. So you're learning a model of, I don't know, probably 10 quantum parameters, or quantum parameters, but quantum control parameters and 1,000 classical parameters together. It takes ages, it takes many days. But here you can actually do it yourself, and it's explained again. And I think that's it. Yeah, let me leave that slide, and I'm happy to take questions if you've got any.
Okay, well, for the first talk in their series, it was awkward to have no applause, but now it seems common, and I'll applaud on everyone's behalf, so not everyone has to.
I can live without.
Is there any questions from the audience?
Yeah, I had a question, Chris.
Don't ask me.
Hi, I'm a PhD student in business group. And apologies, I missed the first 10 minutes of your talk, so you may have touched on this. But I was curious as to, and thanks for the talk, very, very interesting. And I've had a play around with Penny Lane, but I haven't really had a chance to get stuck into the weeds yet. And the answer to this question may be in the read the docs bit on Penny Lane, but I was curious about what advantages you see coming from the quantum part of quantum machine learning for things like back propagation. Are there any benefits that you're seeing or that you've seen in terms of, you know, if you sort of change the back propagation structures of your network, maybe there's some benefits that can be obtained through quantum resources that aren't available classically, or is that something?
Yes.
Yeah.
So that's actually the elephant in the room that I never talk about, because after years I don't find it so interesting anymore as everyone else. You know, you do your research, you don't really think about why the world should fund it. No, I'm joking. So yes, let me answer this from a near-term perspective. When you talk about backpropagation, quantum will very likely not give you any benefit. On the opposite, it might slow you down, not by a nasty factor or something. Let me just explain. So if you if you optimize these variation circuits, you will always have to run your circuit twice for every parameter you want to optimize. So this is a linear scaling, which is not bad in this sense. But backpropagation is actually so famous because it can do better than linear scaling. If you've got 1 million parameters in your network, it doesn't have to run the network 1 million times, but there's a very efficient sharing of information between runs. So it gets away with less. This is something that might be impossible by laws of quantum computing. So what does that mean? If you have a big machine learning pipeline, you have a quantum node there, the quantum node itself will still be part of this efficient backpropagation part, but inside the quantum computation, you're not very efficient. So you might not want to have a lot of parameters in your quantum model. And without thinking about backpropagation in all generality, I think we have been maybe all a bit too excited. I think we have to take a step back there. I'm starting to really think about it very critically and see that so my idea is encoding is the important thing to think about quantum machine learning. There are a lot of encodings that are extremely stupid that people use all the time, where you can just fit sine functions. So, you know, a neural network can fit any function, we can just fit sine functions. And this is probably also why you see the structure here. So, you know, like this encoding is just, well, it's a bit more complicated, but still. So I think we have to start understanding these embeddings. And if we find an embedding that's useful for some task, for example, signal processing or whatever, we might be in business. I don't think in the end that an exponential speedup or intractability argument will run this, but I think there's some things that are very natural for these quantum systems that are very useful for machine learning. And I think the key lies in these feature maps.
Thanks, yeah, it's interesting.
I have a follow-up question. It was related to one I was going to ask anyway. It was, you said that penny lane for this particular example we're looking at here is limited to 1 and 2 qubits. I'm wondering why that is, because you know I can train a network with a million parameters on my desktop. You know what? Why is this so difficult?
It's extremely frustrating. So there are a couple of answers to this. To train so first of all, in this example, obviously there's a class. So let's take this one here. So if you just train the quantum circuit, you can train these variation circuit for like, you know, 10 qubits nicely with a couple of parameters, and people do that. But then it starts getting nasty. So the point is you don't only run your circuit once, but for every parameter, you have to run it twice. So it's 2 times the number of parameters, that's your run, times the number of training epochs, which is sometimes thousands. So that's again another factor. And then in this framework here, this is actually like only in this framework here, you have to measure the overlap of quantum states. So you have quite a lot of, like another factor that comes on top. So you basically have to run your circuit like thousands and thousands of times. And if you have, you know, if every circuit run takes a couple of seconds, that easily becomes days and months. So there's no prohibitive argument why you can't do quantum machine learning easily on 10 qubits in simulators. But effectively, there's like some linear scaling that very quickly comes out of hand.
Right.
And on hardware, oh gosh, like quantum machine learning is done on 1 or 2 qubits at the moment because everything else is too noisy, which is
right.
Heavy.
Thanks.
So I have a related question on this. So if the number of qubits is really small, why do you have to be quantum? Can you simulate this quantum circuit part classically? Or?
Yes, so that's all. So penny lane, no, well, these experiments have been done classically. So this is actually the limit that I'm talking about. If we have quantum devices, all of this will be possible, feasible, and very fast, because a run of your quantum circuit is like really, really quick. If your control loop is also rather quick, which is a bit of a problem at the moment, especially with cloud services. But so the moment you can use quantum devices, you can do this very fast, and then it will be all possible and nice. So when I talk about like we are at the moment limited to very few qubits in simulations, the reason is that it's simulations, and simulations are just like, you know, quantum simulations are just very expensive. And in real devices, the only limitation is the noise and the control loop that might be long. So does that make sense? So we are simulating these things actually.
Yes, like classically you can simulate 20, 30 qubits very easily, right?
Yes, for one circuit. So like someone says, okay, we can nicely do like 30, 40 qubits and they talk about a single run of a circuit, or maybe, yeah, and then calculate like an average of the result or an expectation value. But remember, so when we optimize, so machine learning has this whole like optimization loop. That was what I tried to say. And in every optimization loop, you have to run the circuit a couple of times for each parameter. Then you have to run it in every epoch again. So your constant factors actually add up a lot. So the single circuit, you will have to run thousands of times. And that makes it take long.
Okay.
In every quantum machine learning algorithm, though. Like in classical machine learning, you run your neural networks millions of times, so to speak.
So wouldn't that imply that even when we're running it on quantum hardware, that it would still take a long time? Because, I mean, if you're simulating 1 or 2 qubit circuits classically, I mean, a single run will take, you know, a couple of microseconds, even on a laptop.
Yeah. So, yeah, really the hope is that just this constant time of running the circuit with a lot of qubits will shrink. So, I mean, if you've got 20 qubits, and so I think on most technologies, if you have more and more qubits, as long as your circuit doesn't increase, the runtime should be still the same, right? But that scaling is not true for classical simulation. So that's the problem. If you've got 10 qubits, it's a lot harder than 1 qubit on simulator. But on hardware, we hope that we stick to this constant small time, and then it's doable again. But it is really an open question. Also, this whole like, can we speed up this back propagation in quantum circuits? So, you know, the big ideas are there, and now people are starting to work on these like fine tunings. And if you think about it, neural networks were around in the 40s, and the big breakthrough was back propagation in the 80s. And it was back propagation wasn't a breakthrough because people understood they can like take a derivative of a neural network. But actually the idea was this like very complex automatic differentiation theory that sped things up past like, you know, to better than linear scaling in the parameters. That's a very cool task for a PhD, actually.
Cool, thanks.
Maybe oh, sorry, go.
Okay, sorry. So I want to ask in general. So at the beginning of quantum machine learning, people were claiming about exponential speedups, and I think we understand that this is not possible. So what's actually the advantage of doing all of this? So why just not use the like in the example you explained for a 1 or 2 qubit? Well, I can just use the whole ResNet network and probably I'm done with the job. So is there an advantage of actually going to the quantum, to add this quantum part?
Yeah, so there's 2 answers. So these exponential speedup discussions, they were very much part of early quantum machine learning and this traditional approach. And it's the same as in quantum computing. All the arguments are the same. You know, like for very limited cases under very controlled conditions, there might be exponential speedups, but it's very complex to analyze. It's a bit like if you know the HHL algorithm, like it has its terms and conditions and so on and so forth. So this is a completely different discussion from this near-term stuff. The answer to this question, why are actually bothering? I mean, you sometimes like wonder yourself, but I mean, classical computers were also one day like a couple of bits, right? And the idea is that the quantum computers speed up. There is through the Hilbert space that grows so exponentially, like there's just this big scaling effect. And what we're in after at the moment with these variation circuits, well, we're doing them at the moment because there's nothing else to play around with in real life. So this is the model that's the most realistic for the next years. But also, while we're doing this is not an exponential speedup. Took me, I think last time I was in Sydney giving a talk, I was afterwards a bit embarrassed because I was preaching about this change of mind we have to start in quantum computing to stop thinking about exponential speedups. Because if you think about computer science, 99% of all algorithms are not, you know, they are heuristics, or you can't even prove how good they are. So we have, in my mind, we haven't uncovered 99% of the power of quantum computing that could be interesting, just because we're constantly like nailing people down on the moment someone has an idea, you say, is there an exponential speedup? Can you prove it? And if not, you're already out. And so I've got a very, you know, distinct opinion on that we have to be allowed to play without thinking about exponential speedups. Last little bit I say about this, because I get this question a lot, is also the first part of the talk was really to tell you the task or the goal of machine learning is not to do things fast. I mean, there are limits, but like not to do things fast. The goal of machine learning is to find models that generalize well. So if quantum machine learning is doing a good job, it's not because it's faster than anything classical, or in the end, the first step we have to show is that quantum machine learning generalizes well the models that it gives rise to. In the next step, we can say like, can we do this classically or not? But first of all, we have to uncover this new model class that they have inherent in them.
Yeah, so and so did you do like a comparative study, like in terms of say accuracy or whatever metric, like comparing a pure classical machine learning algorithm and a hybrid algorithm? Is there an advantage in terms of accuracy, not about speed?
Yeah, so we haven't done that, but like there are a lot of studies who do exactly that, and then it's tough. So some of them find yes there is, some of them find no there isn't. But even in machine learning, if you have very small low dimension, so the regime that we are working in at the moment with these like very low dimensional data sets, or even the high dimensional data set, but where the quantum part is so small, it's really hard, because what do you compare to? Do you compare, so this model here, do you compare it now to a neural network that has another layer here, or that has a linear layer on top of this, or that, which nonlinearity do you use? Do you use the same optimizer? Because here you might use a quantum optimizer that's different. So what I'm saying is that these models in this regime that we're looking at are so, have such a big variety of results that it's very, very hard to benchmark them. So I personally think that these benchmark studies are not the right thing to do at the moment, because people then have two curves and they say quantum is better, but they probably just like optimized everything until quantum was better, and it's a very non-robust result. So I think this is dodgy to, or this is a question we can't answer at the moment. I think we should actually like develop theory to answer this question, because our computations can't do it at the moment.
Yeah, okay, thank you very much. Thank you.
Okay, so maybe I'd like to ask a question from an experimentalist perspective then. So I don't know an awful lot about machine learning yet, though I'm interested. And so you're with your expertise in the area, what if I ask you, if you could have one experiment done in the field at the moment, one demonstration of machine learning, what would you choose? What is the thing that you most want to see actually implemented in some sort of physical or experimental system?
So that's hard to answer, but I hope my deviation of the answer will be still satisfactory. If I would have now a lot of labs and I could tell them all what to do, I would say, go check your device and see what feature maps they naturally implement. And now go into the machine learning literature, try to develop theory to check if this is an interesting model. So there's a lot known about these feature maps. So machine learning has something called statistical learning theory, and statistical learning theory is extremely sharp on these kernel methods. So it can tell you quite a lot about the generalization of your model when I give you a feature map or a kernel, which is something equivalent. So I would say like just check your device, what it generally can do very naturally, and then yeah, see if your device can do something interesting, then you can just implement it and show some results on that. And maybe the second answer to an experimentalist is, I also think that this whole quantum machine learning might in the end not be successful in doing machine learning in a long time, but it really changes the way we think about quantum experiments as well. For the following reason, I think a lot of labs have a technology and then they take months and years and decades to develop a C0 gate. And it just turns out in their technologies, everything is nice, but the C0 gate is not nice. In this approach, it's completely different. Give me your device, give me your control parameters, and I start tuning. So we learn quantum algorithms, which means don't worry so much about what gates you can implement, but just worry about how rich the quantum computations are if you give me control over your parameters. I hope that's clear, but I think it's a real big paradigm shift of how to develop quantum computers.
Okay, so but in your first context, where we're talking about go and work out what your device can do and then demonstrate it, is there something from a machine learning perspective or a quantum machine learning perspective, is there some feature of these processes that you would like to see an experiment demonstrate? as opposed to the end application.
I see. So you're basically asking, like, would I already have an idea what a good feature map is that one could check if the device would implement that? Is that the question?
No, I guess I'm saying, like, if I've got my device and I go look and see what sort of feature map can I implement, well, what would I actually be trying to show physically? What would I try to measure to actually to put that in the language of machine learning to make it meaningful in that context?
Yeah, so if your device can measure overlaps, then you could already implement this framework that we have here. So you could kind of, for example, you could measure overlaps of quantum states. If you see these pictures here of these overlap measurements, you could demonstrate that after optimizing some parameters, maybe in your feature map, so some control parameters that are not fixed with the inputs, you can distinguish data. So actually, okay, now I understand your question. So the answer to this is you want a feature map that if you give it a data set of data of 2 different classes, like pictures of ants and bees or whatever, you want them to appear very separate in your Hilbert space. That's what you want to optimize. So you want tight clusters that are far apart from each other in Hilbert space.
Okay, so this identification concept is something that you think is like really that's the thing that we should be working on if we've got some experiment.
Exactly. So if you look at, can you actually see my mouse?
Yep.
Okay, cool. You want this plot here. You want a feature map that implements this plot here. You want the overlaps between data embedded into your Hilbert space from one class to be extremely similar and the other one extremely similar and mutually very dissimilar. So if you can do this plot with very interesting data very naturally, then you're in business, I think.
Okay, thanks.
Well, great. I think lots of interesting questions. That's the hour, so I think it's a good point to stop. And let's thank Maria very much for the excellent talk. And hopefully we can all see each other again soon.
Yeah, perfect. Thank you very much. Thanks for listening.